Okay, let me remind you where we left off talking about dictionaries. The dictionary stores key value pairs. So the key is what we index on in a traditional list, that's 0, 1, 2, 3. In a dictionary, it can be anything including a string. So the dictionary of blue is equal to 460. The dictionary of orange is equal to 600. All right? Now, I posited one possible implementation of a dictionary in which we had two lists, one that stored the key, one that stored the value. In order to find something, you just do a linear search through the key, you find the index, and you go to the corresponding value list, and you get the value. So that would be a nice way to do something if all you cared about was indexing on a string, sort of a clever way. And you could build this. You could build this dictionary with an object class, defining your own class, and it would work just fine. But finding is still costly. You still have to search for something. You got to go through the list. Okay, and what dictionaries are going to afford us through a technique called hashing is the ability to find things much, much more efficiently than having to search the entire list. So imagining the following function. Okay, this is called a hash function f. It takes as input a key, blue, orange, green, yellow, some string, and it returns an index 0, 1, 2, 3. So an integer between 0 and the number of elements in the list. What is that index? Of course, that's where the key is going to be stored. So imagine this function. Don't worry about how I built it or whether it's feasible or not for now. Just imagine I have a function that takes as input the string blue and returns 0. It takes as input the string orange and returns 1, green 2, yellow 3. And let's say that it does that efficiently, so it doesn't cost me big O of n, where n is the length of the list to do it, so it's very, very efficient. And, perhaps most importantly for now, is that the number it produces is unique for each key. So if f of green is 2, f of any other string cannot be 2, because that means there'd be two things being stored at this element, and for now we can't do that. Okay, so what would happen if I had an efficient function f, a hash function, that produced a unique index between 0 and the number of elements in the list minus 1? What would that mean for finding something in a dictionary? Well, if f of blue is 0, and I can compute that efficiently, well then if I want to know if blue, or what the value associated with blue is, well then I simply compute f of blue, it returns 0, and I go in to look in my list and I grab the value associated at position 0. I didn't have to search for blue. I have this sort of magical function right now that will take as input a string and produce an integer index. And if I want to know what the value associated with green is, I would say f of green, it would return 2. I go into the list, grab the value associated with that, and I am home. Okay? Now, that's pretty cool. I mean, we have a lot riding on that function, but now when I go to search for something, I don't have to look for it. So when I ask for my dictionary of green, I don't have to go through this list going green, 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 green. Ah, found it, go to 2, get the value. I simply take green, I shove it into a function, I get the index, and I get the value out. And since that function operates efficiently, this whole thing operates in big O of 1. That function doesn't depend on the number of elements in the list. Now, we don't know where that function came from, so I'm just positing the existence of this function. And if we have it, then we can do something phenomenal, which is we can find something in constant time, no matter how big the dictionary gets. So think about that for a second. Think about, what does it mean that no matter how much information I store, I can find things instantaneously? That is phenomenal compared to linear search, even logarithmic search, as n gets really, really, really big. Google size big, Facebook size big, 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 big data. And so, but now the problem is we don't really know where that function came from and whether it's even feasible, and that's what we're going to talk about next. But if we can do that, we can find things in constant time using these dictionaries and this hashing function. All right, so let's think about what a hash function might look like. Right? What is something that might do what we want? Take as input a key and return an integer 0, 1, 2, 3, 4 up to the length of the list. So here's my first hash function. I will go ahead and admit from the beginning this is a terrible hash function, but we'll talk in a minute why that is. So it takes as input key, and because it must return an index, between 0, 1, 2, 3, and the length of the list minus 1, I'm going to pass in n as a parameter just so I make sure that I don't give it a number greater than n. All right, so this is a little, if you haven't seen this Python command here, this is what's called a type checking command. Assert type is a built-in Python command that takes as input a variable, in our case key, and it's going to ask if the type of key is str, a string, then everything is fine. And if it's not, then flag an error. So this assertion is a command that will allow you to check the data type of a parameter you passed in. If it satisfies it, everything keeps executing, and if it doesn't, it flags an error and exits gracefully out of the function. You should get in the habit of using these. We haven't used it up until now because we're not doing formal software engineering, but as a general rule, you should be in the habit of making sure that users pass in the parameters that you think they're going to pass in. Okay, so we've got a string coming in here. My hash code is going to be that index that I return, which will be 0, 1, 2, 3, 4, up until the length of the list minus 1. I'm going to initialize that to 0. And then I'm going to say for char in key. So key is green. So char will be green. Remember that with for loops, I can treat strings almost the same way I can treat lists. That is, with a for loop at least, I can index into each character of the string. Now what I'm going to do is I'm going to take that character and I'm going to convert it into a number using the OR operator. So the OR operator takes as input a single character and returns what is called the ASCII representation. So the OR of A is 97, the OR of B is 98, and so on and so forth. So every character on your keyboard has a corresponding numeric value. That is internally how these values are being stored and being represented. So these are called the ASCII representation. And since I want to convert my string into a number, this is a natural way to do it. So you can think about that. I could have also converted A to 0, B to 1, C to 2, etc., etc. I just chose to use the ASCII ordering because that's a simple function that does it for me, and I don't have to worry about how to do the conversions. So what am I going to do here? I'm going to take the hash code initialized to 0. I'm going to take every character in the key, green, G-R-E-E-N, convert it into an integer, and sum up all those numbers. Okay? So sum up whatever the OR of G is, whatever the OR of R is, and so on and so forth. And at the end of that, I will decidedly not have a number between 0 and n. And I will not because I'm summing up numbers that are much bigger than, say, 4, for example, if that was our initial dictionary. But they are integers, so that's good. Why do I know they're integers? Because every OR is an integer, every ASCII representation is an integer. So I have an integer here, but it's way, way too big. So to make sure that it's scaled between 0 and n, I'm going to do the obvious thing, which is I'm going to do modular division with n. So I take the sum of all the ASCII representations of my character, I do modular division by n, that guarantees me a number between 0 and n minus 1, because that has to be the remainder after dividing by n, and I return that as the hash code. Okay? Good. Now, let me ask, is it efficient? So we need two things. We need efficiency and uniqueness. So let's talk about efficiency. If I have a dictionary with 1 billion entries, and I ask you to compute the hash function on the string green, is the for loop inside of here have anything to do with the 1 billion entries in the dictionary? Absolutely not. It has to do with the length of that key. Right? So this is efficient. It is big O of 1 with respect to the size of the dictionary. I'm not searching through every element of the dictionary. I never care. So whether I've got 1 billion things in the dictionary or 5 things in the dictionary, the only thing that changes is that n, but that doesn't change this little for loop. So this is very efficient. So that's good news. We need that. Now, what else do we need? We need uniqueness. So if I hash green and yellow and blue and orange and purple and pink and white and black and whatever string I want, they should all come out to be a unique integer between 0 and n minus 1. So is this unique? Well, of course not. Because if I hash rat and I hash tar, I'm going to get the exact same number. So I told you, I confessed early on that this is a terrible hash function. It's efficient, but it absolutely is not unique. Why, by the way? Because the ordinal conversion of these 3 letters is the same as the ordinal conversion of these, just in a different order. And since all I'm doing is summing everything up here, I get exactly the same number. So that's pretty busted. Okay, so that won't work. Well, let's see if we can just do a little bit better. Okay, so what if now, instead of, so this is the same thing. I've got a new hash function, key and n. I'm going to assert to make sure it's a string, initialize my hash code to be 0, and let me initialize p to be 1. P is going to be the position of the character starting at position 1. Okay, so what I'm going to do now is I'm going to convert every character into its ordinal representation, same as before, and I'm going to multiply that by its position. Okay, why am I doing that? Well, that way the TAR and the RAT won't have exactly the same value because the letters are showing up in different order. Okay, and then of course I'm going to increment p by 1. So, is this unique? Am I guaranteed uniqueness? Yeah, probably not. It's still efficient, by the way. I've still got a little for loop here that only runs in the length of the key. It has nothing to do with the size of the database. But you just know you're going to get unlucky somewhere down the line, in large part because of that modular division. Two things are eventually going to collapse onto each other. So this does a little bit better than the previous one, but we're still going to have what are called collisions. We are going to eventually take two strings, and they're going to give me the same index, and now I'm in for a world of hurt. So here's the sad truth. That function that we wanted, that f function that was efficient and unique, probably doesn't exist. Okay? But here's the good news. We don't need perfect uniqueness. We just need distinctiveness. Okay? So we still need efficiency. We're not giving up on big O of 1. I want to be able to find something in my dictionary in constant time. Yep. But that function, to be efficient, we're going to have to deal with the fact that when I give it two keys, K1 and K2, it's going to hash to the same value. And that same value is where something has to be stored, and we're going to have a problem. So we're going to have to resolve the conflict, and here's how we're going to do it. So this is, in fact, how, not all dictionaries are implemented this way, but this is how dictionaries could be implemented. So my hash table, also referred to as a dictionary, so I sometimes call this a hash table because we're doing hashing to get the index from the key. Looks something like this. So here's a dictionary or a hash table with 8 elements in it, just a list. Every list points to, what is this? It's a linked list. Okay? The linked list stores the key value pair, KV, KV, associated with the index at which the key was hashed into. So notice by not just storing a single key value here, but storing multiple key values, I can deal with collisions. So if K1 and K2, if these two keys, because I got unlucky in my hash function, hash to 3, well, it's fine. I'm just going to store both of them. But now we have to ask the question, well, what is that going to do to our runtime complexity when we go to find something? So we'll come back to it in a little bit. And we should also talk about why I chose a linked list here. We'll come back and talk about that in a second as well. All right. Let's first ask, what is the best case scenario for finding something with this implementation? Absolute best case. Well, I could get lucky. I could hash 8 things into the table, and I get lucky, and they each hash one into, each one hashes into a unique index, and every one of these cells only has one element. K1, V1, K0, V1 is up here, K1, V1 is here, K2, V2, up to K7, V7. Best case scenario. Can't guarantee it, but could happen. I could get lucky. So best case scenario then, what is my runtime complexity for finding a key value pair? Well, how do I find something? Shove K into the hash function. Of course, it's deterministic and has to return the same value when it sees the same key. I get an index. I just told you best case scenario is everybody is unique, and I get the value out. Hash function is constant time. Extracting one element, constant time. So best case scenario is I've got big O of 1, right? Good. But I'm not guaranteed best case, and big O is, of course, we're always worried about the worst case. So what's the worst case scenario? How bad can this get? Well, the worst case scenario is the opposite. The worst case scenario is I'm really dumb, and I used a hash function that looks like this. It takes every key, and it hashes it to exactly the same index. Now, why would I do that? Why would I be so stupid? Who knows? I'm having a bad day. So I'm having a bad day. I hash everything into the same value. Worst case scenario is I'm back to linear search. It's big O of n. Why? Well, I take a key, I put it into my hash function. It says 3. I go to 3, and I've got to walk down a linked list of n elements. That cost me big O then. So worst case scenario is not bad. It's still linear search. I haven't done any harm, and I haven't done any good. Okay. Now, the expected case, though, is going to be better than that. So when you design a hash function, you design it to be efficient, run in big O of one time, and to minimize collisions. And because we don't have time in this class to talk about what those hash functions look like, I won't describe them. But those hash functions are relatively straightforward to design, and there are well-known hash functions for doing that, so that when you hash into it, and there's other tricks that you do to make sure you minimize collisions. So the way, when you build a good hash function, we can guarantee that the worst case scenario is going to be m. So it's not 1. There isn't just one element here. But m, as in Mary, is much, 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 much less than n as in Nancy, which is the entire set of elements in the list. So we can get to close to something that is constant time if we have a smart hash function and if we implement the dictionary in a clever way so that there are minimal number of collisions in an entry. So that when I go to search for a key, if there is more than one here, well then I just have to search a small number of them, and that's very, very fast because I don't have to worry about everything stored in the 0, 1, 2, 4, 5, 6, 7, etc. positions. But why did I pick a linked list? Did I have to, first of all? No, I could have done something else. I could have done a list with a key value pair in there. But the reason I did, in this case, a list is because if my dictionary is dynamic and I want to add and remove things, we know that adding and remove things in a linked list is more efficient than a list. And so we store these more dynamically. And of course, I could have made this both a circular list or a doubly linked list or whatever it was. Okay, so that is a dictionary with a reasonably clever hash function that is efficient, runs in constant time, and distributes the indices for all possible keys nice and uniformly distributed across your table, your hash table, your dictionary. You can find things in constant time or near constant time. And that is sort of magical. And by the way, without that data structure, we would not have Googles and Facebooks. We would not be able to index into these phenomenally large databases so efficiently. So not only are these databases huge, but we're doing millions of queries every second. So even something that is logarithmic, which is very, very good, is still going to be rate limiting if you have massive databases and a massive number of requests. So being able to do things in constant time or near constant time is incredibly efficient. And it all comes down to that very clever idea of a hash function, push strings into distinct values, and then a little bit of cleverness on how to deal with collisions when your hash function isn't absolutely perfect. Okay, we have 2 more things to do. We're going to do a drill, and then we're going to do the full-blown runtime complexity comparing lists, linked lists, and dictionaries. So we'll pick it up in a few minutes.